This lesson is about linear and angular velocity. This lesson is more of a physics application of trigonometry. I'm putting it in here as an introduction to those of you who are going on into a physics course and to get you thinking about different applications that we can use what we've learned. So as an application, I decided to come up with an example that I'm aware of that linear and angular velocity apply. And here's what I came up with. So imagine you're riding on an inner tube behind a motorboat, and you're connected by a rope. When the boat is traveling straight, you're traveling at the same speed as the boat. That should make perfect sense, because if the boat is going, 25 miles per hour, you're being pulled, straight with a rope, then the inner tube behind it is also going the exact same speed. Now, imagine that the boat makes a turn. Are you now traveling faster than the boat, at the same speed as the boat, or slower than the boat? And if you really think about this, the boat probably would have to slow down in order to make a sharp turn. And so it would seem that you on the inner tube would be traveling then slower, but because of what happens with angular velocity, you actually travel a whole lot faster than the boat. We'll dive into this further as we discuss how linear and angular velocity work. Let's begin with linear velocity. Linear velocity is very simply defined as v equals s over t, where s is the distance traveled, v is the linear velocity, which you could think of as speed as long as you don't include a direction. So speed is how fast you're moving. Velocity is your speed plus a direction. So if you're not considering direction, you can call it speed. And t is the amount of time. So very similar to, the formula distance equals rate times time. We just have this solved for r, basically. So the distance divided by the amount of time is the rate at which you're moving. We're just now calling this velocity and then using s for distance instead of d. So very simple. With angular velocity is the rate at which an object is rotating, which is defined as omega equals theta over t, where theta is the angle in radians through which the object rotates, t is the amount of time it takes to rotate, and omega is the angular velocity. This omega is just another Greek letter that we have to use here for this particular example. It doesn't have any special meaning itself, it's just a letter that we use for angular velocity. Since s is equal to r times theta, so s is arc length, that is. We learned that arc length is equal to the radius of a circle times the angle measure that's intercepted by that arc. So arc length is s times theta. Arc length is s equals r times theta. We learned in an earlier section. But because we know that, we can substitute this into the linear velocity to get. So linear velocity is s over t, which means I could say linear velocity is r times theta divided by t. Now keep in mind, all of this, since it's dependent upon arc length, we have to make sure theta is in radians. But since omega equals theta divided by t, we can say that velocity equals r times theta over t, which is equal to r times theta over t, or r times omega. So velocity is equal to the radius of the circle times the angular velocity. So linear velocity and angular velocity are related by the radius of the circle. This happens a lot in physics, where you have a couple of different formulas that are related, but you can combine them into other formulas that are, in some cases, more useful, which is what I've done here. So certainly the definitions for linear velocity and angular velocity are helpful, but this formula that represents the relationship between linear and angular velocity is what we end up using quite a bit more. Let's talk about the difference between linear and angular velocity. The difference between linear and angular velocity is that the angular velocity of a rotating object is constant, whereas the linear velocity of that rotating object is different depending on the radius of where you're measuring. Okay, so let's look at a conceptual example here. So I have a wheel. On this wheel, I'm going to pick a point and I'm going to call it P1. Now I'm going to rotate this wheel and we're going to watch what happens with that point P1. So as I rotate the wheel, this point P1 rotates in basically a circle. So it would kind of rotate along this kind of a path right here. So notice how it kind of traces out that path that I've drawn approximately, right? Obviously it's not perfect. Okay, so it travels along that particular path there. Now let me draw another point, which I'll call P2. And I'm going to rotate the circle again and show you what happens next. So now as I rotate point P2, I kind of map out, this circle here, which is just, it's a little bit bigger. And as I go all the way around, it's kind of hard to do. I'm just going to estimate it from here. As I go all the way around, I map out a circle, but it's a larger circle. So P1 and P2, they were rotating around the center point of rotation at the exact same speed, at the exact same angular velocity. So the angle with which they rotated was the same. So for instance, we started basically at an angle measure of, say, like 30 degrees. In the same amount of time, these things get over to 90 degrees at the exact same time. So they're going through the exact same angle measures during the exact same period of time. So their angular velocity is equal. What's different is their linear velocity, because linear velocity is equal to basically, think about distance equals rate times time. So the time is the same. So let's say it took me 4 seconds to get around the circle. The distance, however, is different. So the distance for the first point is obviously smaller than the distance for the second point. So the distance for point 1, maybe it's, let's say 12 inches. And the distance for the second point, let's say, is 24 inches. When I divide both sides by 4, the rate of point 1 is 12 over 4, which is 3. The rate of point 2 would be 24 over 4, which is 6. So the linear velocity of point 2 is higher because it's further away from the center point of rotation, which is shown in the formula that we developed in the last slide, that the linear velocity is equal to the radius times the angular velocity. So the larger the radius becomes, the larger the linear velocity is, even though the angular velocity is constant all the way around. So that's the difference between linear velocity and angular velocity. Let's look at some example problems. It takes approximately 24 hours for the Earth to rotate on its axis. Find the angular velocity of the Earth measured in radians per hour and calculate the linear velocity of a point at the equator. You may assume the radius of the Earth is 3,959 miles. All right, so in order to work through this, we just have to kind of, gather our formulas that are necessary. So things that we know are the angular velocity is equal to theta divided by t, so the angle with which we rotate in a period of time. And the linear velocity is times omega. Okay, so we have enough information to derive what the angular velocity of the Earth is. So let's take a look at that. So the angular velocity is the angle with which we rotate through and the amount of time it takes to rotate through that angle. So we know it takes about 24 hours to do a complete rotation of the Earth. So that's what we're going to work with. So an entire rotation would be 2 pi. So I'm using radian measure here instead of degrees because all of these formulas require radian measure. The amount of time it takes to rotate through that angle is approximately 24 hours. So the units that we have here, radians in the numerator and hours in the denominator. So this becomes, let me grab the calculator. So if I take 2 pi divided by 24, I get 0.262. Well, I'll just use 3 decimal places. Follow any rounding rules that you're provided in homework. So 0.262. And we'll call that radians per hour. Now, so the angular velocity is constant, but the linear velocity is different. And so they're asking us to find the linear velocity, basically the maximum linear velocity, because it's looking at a point on the equator. So at the equator, we can assume the radius of the Earth is 3,959 miles. So the linear velocity of the Earth at the equator is the radius at the equator multiplied by the angular velocity. So, getting the calculator out, I'm going to just hit multiply 3959. And the reason for that is, depending on the homework system that you might be using, there may not be any rounding performed until the final operation. So anytime you give an answer, it's okay to round that answer to provide it. But if you're using that value in the next calculation, it's probably safest to not round the number off. So for instance here, I get approximately 1,036 So the radius we had in miles, and we were doing this per hour, so this would be 1,036 miles per hour. Now, if I had used the rounded number, 0.262 times 3959, it comes out to something slightly different. And so when you're doing online homework, for instance, or even checking answers in the back of the book, you may find that your answers are just slightly off because of rounding issues like this. So that's probably the root of it. If you use a rounded value within your calculation, you may get slightly different answers in the end. So whenever you're asked for an answer, go ahead and give the rounded value. When you're going to use that in a later calculation, try and use the unrounded value. So use as many decimals as you can use. Okay, so what this means is even if you're standing still at the center of the Earth, you're already moving 1,036 miles per hour, just standing there. Pretty incredible, huh? Now, here's a bonus question. Why is Florida chosen as the location of where NASA launches rockets into space? Well, turns out there's a couple of reasons, but here's one really good reason. And unfortunately, I didn't have a graphic that showed Florida, but that's okay. You kind of see a little speck of it right there. So here's the thing. So Earth rotates on a tilt, but I'm going to kind of ignore the tilt, and I'm just going to use a north and south pole here. So Earth is going to rotate on this north-south pole. Now, when it's rotating, that's the axis of rotation. So when you calculate linear velocity based off the Earth's constant angular velocity, the linear velocity changes per latitude. So for instance, the distance that a point travels near the North Pole is a whole lot shorter than the distance that a more southern point would travel in the same amount of time. So at this first longitude, which latitude I'll call L1, and the second latitude I'll call L2, a particular point at L2 is traveling faster than at L1. And it's going to maximize near the equator. And I'm just approximating where the equator is here. But that's going to be the maximum speed because that's the maximum radius away from the axis of rotation. And as you go more southerly, you start getting smaller and smaller radiuses, which means the linear velocity is smaller. Now, Florida, in terms of the continental United States, that is the closest point to the equator, which means Florida is rotating faster than most other points on the United States. So when you are shooting a rocket out into space, you need all the help you can get because you have a lot of weight of the rocket, a lot of weight of fuel, and by getting this little boost of about, it would be less than 1,000 miles per hour, but at Florida because it's not at the equator, but getting that boost of approximately 1,000 miles per hour from just because of the Earth's rotation, that's a great big help. And it wouldn't make a whole lot of sense to use a point in near the North Pole or the South Pole because you just wouldn't get that boost to start with. So that's a pretty cool application of angular velocity, I think. So suppose we have a boat, that's traveling along, and it's going to rotate about this particular point right here, right in the center of the boat. All right, and then, I'll make this just kind of the circle of rotation that it can go through. Okay, so if it's going to rotate 120 degrees, it's going to rotate from here over to here. Our setup basically doesn't take into account like that the boat is moving already, so that it's already going 7 meters per second. It only takes into account that the boat is rotating. So when you have, this person out here on the inner tube, sitting there, it's kind of like the inner tube would be connected not with a string, but something that is taut, like a pipe of some sort, and would rotate the exact same number of degrees, as the boat at the exact same time. So things are a lot simpler in these physical setups than what's met with a lot of applications. So what we're going to do is we're going to ignore that the boat is already traveling 7 meters per second, because that complicates the problem. It complicates it actually quite a bit. You have to use like vector analysis in order to calculate, the angular velocity. So we're just going to assume that a boat rotates 120 degrees in 4 seconds, and we want to see the effect on the inner tube that's connected, 20 meters away. So we have this inner tube that's 20 meters away. How fast is that rotating? So let's begin by getting the boat's angular velocity. So the angular velocity is the angle through which you rotate and the amount of time it takes to rotate that amount of angles. So the angle is 120 degrees. The amount of time is 4 seconds. But angular velocity only really works if you're dealing with radians. So we just need to convert that into radians. So I'm going to multiply this by 180 degrees on the denominator so that the degrees cancel out, and then pi radians in the numerator so that I have radians in the numerator, seconds in the denominator. And so my angular velocity will be measured in radians per second. Okay, so let's see what happens here. So there's a 0 in each of these. You can cancel the 10. 12 and 18 share a factor of 6. So 6 goes into 12 2 times, into 18 3 times. 4 and 2 share a factor. So this is effectively pi over 6 radians per second. And if we want to approximate that, we absolutely can. Just grab your calculator and clear that out. So pi over 6 is 0.524. That's what we'll go with. So approximately 0.524 radians per second. Okay. Now, the linear velocity of the boat we're completely ignoring. We're just assuming that the boat is still. We're just going to ignore that it's moving 7 meters per second. We're going to look for the linear velocity of the inner tube based off of this angular velocity. So the linear velocity of the inner tube is going to be the radius, so the distance away from the point of rotation, times the angular velocity. So 0.524. And when I multiply that, I'll just take that number right there times 20, because again, it's entirely possible that if you use rounded numbers that you might get a slightly different answer. Here it's the same number to the first decimal, but to the second decimal, depending on how accurate the final answer needs to be, the second decimal is slightly different. So that would be approximately, let's just say 10.5. I'll round it to the first decimal. 20, that's measured in meters. So meters per second. So 10.5 meters per second. If you don't know how fast that really is, which neither do I don't really think in terms of meters per second all that easily. If you want to change it into miles per hour, there's about 2.24 miles per hour in 1 meter per second. So if you multiply 10.5 times 2.24, that's about 23.5 miles per hour. So just to kind of give you a little frame of reference of how fast it's moving. So if you think about that, the boat's not moving at all, and here you are out on the inner tube already going 23 miles per hour. So if you add that the boat's moving and rotating, maybe even a longer chord, you could be going pretty fast with just a minimal change in direction of the boat. Okay, another example. Earth rotates around the sun in a nearly circular path. If it takes 365 days approximately for the Earth to rotate around the sun, find the angular velocity of the Earth measured in radians per hour. And assuming that the Earth is 93 million miles from the sun, find the linear velocity of the Earth. So how far in miles does the Earth travel in a day? All right, so here we have a diagram of the sun and the Earth rotating around the sun. Obviously, not anywhere near to scale. But the distance between the sun and the Earth, we are assuming to be about 93 million miles. And the amount of time it takes to rotate around the sun is 365 days. So we can calculate the angular velocity, because that's going to be the angle through which you rotate and the amount of time it takes to rotate through that. So one complete rotation is 2 pi radians. The amount of time to do that is 365 days. So what we're going to have here is this in radians per day. Now, that's all well and good, but it did ask us to find the angular velocity in radians per hour. So to change days into hours, what I'm going to do is just figure out, I want the unit day to cancel out, and I want to leave the unit hour. So I can cancel this out, and I know that in 1 day there's 24 hours. So effectively, I'm going to do 2 pi over 365 times 24. And I'll go ahead and just approximate that. So clear everything off. 2 pi divided by 365 times 24. I get 7.17 and then e minus 4 at the end. So remember, this represents scientific notation. So it's the same thing as like 7.17 times 10 to the negative 4th power. Or you would have 3 leading zeros, so 0.000717. And this would be radians per hour. Okay. Now, the linear velocity of the Earth, so how fast it's traveling in miles per hour. So it's going to be the radius, so 93 million, and that's in miles, so that's the unit that we want in the end, and it's going to be multiplied by 0.000717 radians per hour. So in the end, we'll have miles per hour. So let me get the calculator out. And I'm just going to take this answer and multiply it by 93 million. So about 66,705 miles per hour. So think about that. The Earth itself is rotating, and we discovered that if you're standing at the equator, you're rotating at about 1,000 miles per hour. But then you take into account that the Earth is rotating around the sun. Well, we're traveling at 66,705 miles per hour around the sun. So if that's how many miles we travel in 1 hour, there's another question on here that says, how far in miles does the Earth travel in a day? So distance is rate times time. So the distance that we want to calculate is going to be the rate, which is 66,705 miles, times the amount of time. So this is miles per hour. If we want to travel 1 day, we have to travel 24 hours. So the distance that we travel in 1 day is that times 24, or about 1.6 million miles. So 1,600,921 miles. So just by standing still and doing nothing, in 1 day you're going to travel about 1.5 million miles because you're rotating around the sun in that way. That to me is quite fascinating.